Welcome everyone. In the previous videos, we have discussed the power gain and the stability of the microwave amplifier based on the scattering parameters of the microwave transistor. Now we are going to discuss how to design a single stage amplifier to obtain maximum gain. As we said, maximum gain can be obtained if the load and the source are matched to the transistor. So, assuming that the load and the source have characteristic impedance Z0, which is the same as the Z0 of the transistor, or the Z0 which has been used to calculate the S parameter of the transistor. So it is required to introduce an input matching network and an output matching network to make the reflection coefficient seen from the source is conjugate to the reflection coefficient seen at the input port of the transistor, and to make the reflection coefficient seen from the load is conjugate to the reflection coefficient seen from the output of the transistor. So the condition for maximum gain is that gamma in should equal the conjugate of gamma source, and gamma output should equal the conjugate of gamma load. In the general case, gamma in equals S11 plus S12 S21 multiplied by gamma load over 1 minus S22 gamma load. We have already proved this relation. In a similar way, gamma output in the general case is S22 of the transistor plus S12 S21 multiplied by gamma source over 1 minus S11 gamma source. For a special case of unilateral amplifier, we said that unilateral amplifier means that there is no feedback from the output to the input. Or in other words, the value of S12 is 0. So for a special case of unilateral amplifier, gamma input, it would be S11. And gamma output, it would be S22. Because the value of S12 here, it would be 0. And S12 here is 0. So, for the special case of a unilateral amplifier, if we are interested in finding out or designing out a maximum gain amplifier, in this case, the value of gamma source should be S11 conjugate, because gamma in is S11. And gamma load should be S22 conjugate. So we say that the gain of the input matching network is obtained in terms of the reflection coefficient at the input of the source, which is 1 minus gamma source squared over 1 minus gamma input multiplied by gamma source squared. And the gain of the load, or the gain of the matching circuit of the load, is 1 minus gamma load squared over 1 minus S22 gamma load squared. Now, for the case of unilateral, in the case S12 is 0, gamma in, it would be S11, and gamma output, it would be S22. In addition, for the case for maximum gain, gamma source, it would be the conjugate of gamma in. So gamma source, it would be S11 conjugate. And gamma load, it would be gamma output conjugate. So gamma load would be S22 conjugate. By combining these two relations, we can say that, okay, the transducer gain of such single stage amplifier, as we said, the transducer gain is the available power at the load to the maximum available power from the source. And we said that we are interested in finding out the transducer gain. So the transducer gain is simply the gain of the input matching network GS multiplied by the gain of the transistor multiplied by the gain of the output matching network. So the transducer gain is GS multiplied by G naught multiplied by GL. And by taking into consideration gamma N is S11 and gamma source for maximum gain, it would be gamma N conjugate. So is S11 conjugate. S11 multiplied by S11 conjugate, it would be 1 minus S11 squared. So this would be 1 minus S11 squared. In a similar way, this is S22 multiplied by gamma load. Gamma load for maximum output, it would be gamma output conjugate, and gamma output for unilateral, it would be S22. So this would be 1 minus S22 multiplied by S22 conjugate, which is 1 minus the magnitude of S22 squared. Alright? So from this, we can say that the maximum unilateral gain is 1 over 1 minus S11 squared multiplied by, sorry, here we say that the gain of the transducer of the unilateral gain, the transducer unilateral gain is 1 minus gamma is here, it would be S11 over 1 minus S11 squared. So the unilateral gain, it would be S21 squared. The unilateral gain, it would be S21 squared in this case, because GS it would be unity and GL it would be unity. But assuming that there is no reflection from the output matching network, so we have matched here, so gamma L is 0, and we have matched here, so gamma source is 0. So the maximum unilateral gain is 1 over 1 minus S11 squared multiplied by S21 squared multiplied by 1 over 1 minus S22 squared. This is the maximum unilateral gain. The conventional unilateral gain, GTU, it would be S21 squared only. Alright? To design the microwave amplifier, at the beginning we should check the stability of the transistor. So after the stability of the transistor has been determined and the stable region of gamma source and gamma load are located on the Smith chart, the input and output matching section can be designed. The value of G naught, which is the transducer gain of the transistor itself, G naught is fixed for a given transistor. The overall transducer gain of the amplifier can be controlled by the gains of the source and the load matching networks of the matching section, GS and GL. Maximum gain will be realized when these sections provide conjugate matching between the amplifier source or load impedance and the transistor. This means that maximum gain will be obtained when gamma load is conjugate of gamma output and gamma source is conjugate of gamma input. The maximum transducer power gain is also sometimes referred to as the matched gain because the maximum transducer power gain is obtained when both the load and the source are matched to the transistor from the output and the input of the transistor. Because most transistors exhibit significant impedance mismatch, which means that the magnitude of S11 and S22 are large, the resulting frequency response may be narrow or may be narrow band. This means that we are going to design an input matching network and output matching network to make the output of the transistor matched to Z node and the input of the transistor matched to Z node. Effectively, because the large mismatch here, this input matching network and output matching network in this case will be very sensitive to any change in the frequency. This will result in narrow band behavior. So I can introduce excellent input matching circuit and excellent output matching circuit at a specific frequency. But once I deviate from this frequency, there will be large mismatch between the source and the transistor and the load. So the condition for maximum gain will not be satisfied anymore. So the design of maximum gain amplifier will result in a narrow band amplifier. And as we will see in the following video, to increase the bandwidth of the amplifier, it would be required to design the amplifier below the maximum gain. Below the maximum gain, it means that the input matching network and output matching network will not be perfect matched. Okay? Alright. What will be the situation if the transistor is bilateral? If the transistor is bilateral, it means that the value of S12 is not 0. In this case, we are going to use the original equations of gamma input and gamma out. So the original equation for gamma input is that S11 plus S12 S21 gamma L over 1 minus S22 gamma L. And gamma output, the original equation, it is S22 multiplied plus S12 multiplied by S21 multiplied by gamma source over 1 minus S11 gamma source. And to obtain maximum gain, the gamma input should equal the conjugate of gamma source and gamma output should equal the conjugate of gamma load. This means from this we have an equation which relates gamma source, gamma load and the S parameters of the transistor. And we have a second equation which relates gamma load to gamma source and the S parameters of the transistor. In other words, we have two equations in two unknowns. The two unknowns are what is the required gamma load and gamma source to make the transistor introducing maximum gain. What is the value of gamma load and gamma source which are required to introduce maximum gain? Okay? These are the two unknowns, gamma source and gamma load. And the scattering parameters of the transistor represent constants in this case. So we can rearrange these two equations and solve them to find out the value of gamma load in terms of the S parameters of the transistor only and gamma source in the terms of the S parameters of the transistor only. So by solving these two equations simultaneously, we can find gamma source and gamma load as a function of parameters. These parameters depend only on the S parameters of the transistor. So these parameters depend only on the S parameters of the transistor. So in this case, the value of gamma S, which will satisfy the maximum power gain, equals B1 plus or minus square root B1 squared minus 4 the magnitude of C1 squared over 2C1, where B1 is 1 plus S11 squared minus S22 squared minus delta squared. C1 equals S11 minus delta S22 conjugate, and delta is S11 multiplied by S22 minus S12 multiplied by S21. In a similar way, gamma load is B2 plus or minus square root B2 squared minus 4 the magnitude of C2 squared over 2C2, where B2 is 1 instead of S11 here, S22 minus S11 squared minus delta squared, and C2 instead of S1 here, it would be S22 minus delta S11 conjugate. Okay? Actually, we take the sign plus or minus such that the value of gamma L, the magnitude of gamma L is less than unity. So, according to the magnitude here, we determine which sign will be taken into consideration for physical interpretation. Okay? So, for the case of bilateral transistor, there is a value of gamma source and gamma load which will satisfy the maximum gain. Once again, if we are interested in finding out the corresponding gamma source and gamma load for unilateral, simply we are going to put S12 to 0. So in this case, delta it would be simply S11, S22. By doing this, we simply find out the value of gamma source. In this case, is simply the magnitude, or is S11 conjugate. Is gamma source here, it would be simply S11 conjugate, and gamma load here, it would be S22 conjugate. So you can prove it by letting S12 going to 0 and solving these equations. You will find that gamma source is simply S11 conjugate and gamma load is S22 conjugate, which was originally these relations. Alright? Okay. Now, for the case of bilateral transistor, we have already obtained gamma source and gamma load. Now, we can obtain the gain, or the unilateral, the transducer gain, by setting the gain of the input matching network 1 minus the magnitude of gamma source squared over 1 minus S11 multiplied by gamma source squared, and gamma load, the transducer gain of the matching of the output matching network is 1 minus gamma load squared over 1 minus S22 multiplied by gamma load all squared. And already we have the transducer gain of the transistor is S21 squared. Now, by calculating gamma S and gamma load, we can calculate GS and G load. By multiplying GS by G naught by G load, we can find the transducer gain. So, the transducer gain in this case is the multiplication of these three terms. For the case of matched load for maximum gain, we can prove that the maximum transducer gain for the case of bilateral transistor is the magnitude of S21 over the magnitude of S12 multiplied by K minus the square root of K squared minus 1, where K is already the stability test condition. If you remember, the stability condition, it was based on K delta. When K is greater than unity and delta is less than unity, the transistor is stable, where K is 1 minus the magnitude of S11 squared minus the magnitude of S22 squared plus delta squared over 2 the magnitude of S12 multiplied by S21, and the magnitude of delta is the magnitude of S11 multiplied by S22 minus S12 multiplied by S21. So from this, we can find the maximum transducer gain for the case of bilateral transistor. Once again, if we are going to set S12, the limit of S12 tends to 0, we can find the limit value of K here in terms of this value of delta. Delta would be the magnitude of S11 multiplied by S22. So in this case, by taking the limit when S12 tends to 0, we will find that the transducer gain, the maximum transducer gain, is simply the magnitude of S21 squared, which was originally obtained here. The transducer, sorry, S21 squared multiplied by 1 over 1 minus S11 squared multiplied by 1 minus S22 squared. So by taking the limit S12 tends to 0, we obtain this relation once again. Alright? Okay, so we have obtained the transducer gain for single stage amplifier for both unilateral and bilateral transistors. It should be noted that for stability condition, the value of K must be greater than unity and the value of delta must be less than unity. So at the edge of the stability, the value of K is unity. So at the edge of the stability, this would be 1 minus square root 1 minus 1. So it would be simply S21 over S12. And effectively, this is the maximum transducer power gain which can be obtained by a bilateral amplifier. So the maximum stable gain defined as the maximum transducer power gain with a value of K equals unity, and this has a magnitude S21 over the magnitude of S12. This is the design equations for single stage bilateral amplifier to obtain maximum gain. In the following video, we are going to present a numerical example for such single stage bilateral amplifier to find out how to design this input matching network and output matching network and how to obtain the gain in this case. So see you in the next video.